Hello everyone. Today we will study dot gain measurement. Dot gain value. The dot gain value ZD is also known as the dot gain rate. First, definition of the dot gain value ZD. The dot gain value refers to the difference between the actual area coverage rate FD of the dots on the substrate and the actual area coverage rate FF of the dots at the corresponding position on the printing plate, also known as the nominal area coverage rate of a certain dot block on the control strip, represented by the symbol ZD. Then, ZD equals FD minus FF. For pressure printing, dot gain is inevitable. Since offset lithography is an indirect printing method, its dot gain situation is more serious than other pressure printing methods. Conversely, for offset lithography, measuring and controlling the dot gain value is of course particularly important. Second, detection of the dot gain value ZD. There are various methods for detecting the dot gain value. The following three methods are relatively accurate. 1. Delta value method. Use a high-power magnifying glass with scales. The scale is 0.001 to 0.01 mm. To observe the sizes of the corresponding dots on the printing plate after exposure and on the substrate after printing. For round dots, as shown in the figure, delta equals R sub 2 minus R sub 1. 4 minus 8. R sub 2, the radius of this round dot on the substrate after printing, centimeter. R sub 1, the radius of a certain round dot on the printing plate after exposure, centimeter. In the formula, delta, the increment in the radius direction of the round dot, centimeter. For square dots, delta equals the quantity b sub 2 minus b sub 1, all divided by 2. In the formula, b sub 2, the side length of this square dot on the substrate after printing, centimeters. b sub 1, the side length of a certain square dot on the printing plate after exposure, centimeters. Delta, the unidirectional increment of the side length of the square dot, centimeter. On the premise that the printing conditions, such as the substrate, ink film thickness, ink water balance, and printing pressure remain unchanged. For dots with different dot area coverage rates, different dot shapes, and different screen line counts, lines per centimeter, delta is a constant. Under the condition of a constant delta value, the dot gain values Z sub D of commonly used dot shapes, such as round and square, etc., with different screen line counts and different area coverage rates can be calculated. Through comparison, it will be found that number 1, on the premise that the screen line count and dot shape are the same, the square dot with an area coverage rate of 50% has the largest gain value. Number 2, under the condition that the dot shape and dot area coverage rate are the same. The higher the screen line count, the larger the dot gain value. Number 3, under the condition that the dot area coverage rate and screen line count remain unchanged. The round dot has the smallest gain value. The fundamental reason for the formation of these three important characteristics is that, within a unit area, 1 cubic centimeters, the larger the sum of the lengths of the dot edges, the larger the dot gain value, and vice versa. 2. Murray-Davis formula method. For example, measured by a color reflection densitometer. The density of the white paper is zeroed as d sub W equals 0.00 to eliminate the influence of the paper's grayscale and color cast. The solid density of a certain primary color d sub S equals 1.6. The dot density value d sub T of the dot with a nominal area coverage rate of F sub F equals 75% is 0.9. Then the actual dot coverage rate F sub D is obtained by formula 4-10. F sub D approximately equal to 89.7%. The dot gain value Z sub D at this place is 89.7% minus 75% equals 14.7%. If the solid density D sub S value of a certain color and the dot area coverage rate F sub D value of this color are known, The dot density value d sub t can also be obtained by the transformation formula of Murray-Davis. For example, given d sub s equals 1.6, d sub w equals 0.00, f sub d equals 70%. Then the density value of this dot is d sub t approximately equal to 0.5. 3. Yule-Nielsen formula method. The difference between the Yule-Nielsen formula method for measuring the dot gain value and the above-mentioned Murray-Davis formula method is that when the latter calculates the z sub d value, it combines the mechanical dot gain and the optical dot gain, referred to as light bleeding for short, to obtain the dot gain value, without eliminating the light bleeding factor. The Yule-Nielsen formula removes the influence of light bleeding and only considers the effect of mechanical dot gain. In the formula, n, the Yule-Nielsen correction coefficient; d sub s, the solid density of a certain color; d sub t, the main density of the dot with a nominal coverage rate of ff for this color. For example, measured by a color reflection densitometer, the solid density d sub s of a certain cyan ink is 1.6, and the main density d sub t at the cyan dot control block, with a nominal coverage rate of 70%, is 0.9. According to the Murray-Davis formula method, the actual coverage rate of the dots at this place is f sub d approximately equal to 89.7%. The dot gain value is z sub d equals f sub d minus f sub f equals 89.7% minus 70% equals 19.7%. If the Yule-Nielsen formula method is used, and the Yule-Nielsen correction coefficient n equals 1.5 is known, then f sub d approximately equal to 82%. The corresponding dot gain value z sub d is z sub d equals f sub d minus f sub f equals 82% minus 70% equals 12%. The z sub d equals 19.7% obtained by the former is actually the result of the combined action of mechanical dot gain and light bleeding, optical dot gain. The z sub d equals 12% obtained by the latter is the pure mechanical dot gain, after eliminating the influence of light bleeding on the geometric area coverage rate. The so-called light bleeding phenomenon is that when the incident light is projected onto the printed sheet, a part of it enters the interior of the substrate and diffuses partially there. The part of the light under the ink film of the impression is absorbed, resulting in an increase in the reflection density d sub t. Therefore, the z sub d value obtained by the Murray-Davis formula is essentially the combined result of the two types of dot gain. The magnitude of the light bleeding effect depends on the light diffusion degree of the substrate, the screen line count, the dot shape, the dot coverage rate, and the measurement aperture of the color reflection densitometer. In order to make the test data comparable to a certain extent, it is necessary to uniformly specify as many of the above factors as possible. It can be seen that the Yule-Nielsen correction coefficient n is a quantity reflecting the degree of light bleeding. The better the light diffusion performance of the substrate and the higher the screen line count, the larger the n value. The determination of the n value needs to be determined through repeated tests according to the differences in the substrate, dot size, dot density, screen line count, ink and plate making conditions. When n equals 1, the Yule-Nielsen formula becomes the Murray-Davis formula. 4. Derivation of the Murray-Davis formula. Assume that the dot area rate of the ink printing is A, and the absorption density is infinite, that is, there is no reflected light, and the blank part of the substrate, such as paper, is all reflected, that is, there is no absorption. Then its reflectance is 1 minus A. For different solid densities d sub s, there will always be a corresponding reflectance rho subscript s. As shown in the above figure, the resulting reflectance is a rho subscript s, and the total reflectance of the sum of the two parts is rho equals open parenthesis 1 minus a close parenthesis plus a times rho subscript s. D sub s equals the logarithm base 10 of 1 over rho sub s. Rho sub s equals 10 to the power of negative d sub s. D sub t equals the logarithm base 10 of 1 over 1 minus a times the quantity 1 minus 10 to the power of negative d sub s. 10 to the power of d sub t equals 1 over 1 minus a times the quantity 1 minus 10 to the power of negative d sub s. 1 minus a times the quantity 1 minus 10 to the power of negative d sub s equals 10 to the power of negative d sub t. A equals the quantity 1 minus 10 to the power of negative d sub t over the quantity 1 minus 10 to the power of negative d sub s. Because when the unprinted white paper is measured with a DNSITOMETER, its reflection density d sub w equals 0.00 should be used as the zero calibration reference. That is to say, the Murray-Davis formula, 4-10, is derived from the definitions of the solid reflection density d sub v, the white field reflection density d sub w, and the proportion g of the dots in the unit area. The physical meaning of its mathematical formula is clear. However, when using a DNSITOMETER to measure the dot density, it is inevitable to include the light bleeding factor, resulting in the situation that the measured f sub d value is greater than the theoretically calculated value. As mentioned before, dot gain printed products are first of all visual commodities, the comprehensive result of two types of dot gain: mechanical dot gain and light bleeding, also known as the geometric area, expansion of dots, and optical dot gain. The comprehensive result of the two types of not only inevitably enters the receiver of the densitometer, but also inevitably enters people's eyes, causing a visual effect. Therefore, the Murray-Davis formula method for measuring the dot gain value does have its practical value. Third, calibration of the dot gain value Z sub d. 1. Factors affecting the dot gain value Z sub d. In addition to being related to the ink film thickness delta, dot shape, screen line count, dot area coverage rate, and printing paper, the tolerance range of Z sub d is also related to conditions such as the impression method, the nature of the packing, and the ink-water balance. 2. Calibration of the dot gain value Z sub d. The calibration of Z sub d is also related to the product grade and the smoothness of the substrate. When the product quality requirements are high and the substrate with high smoothness is used for printing, Z sub d needs to be controlled within a small range to meet the printing quality requirements. At this time, it is essential to measure the dot gain values of each tone level before printing and make pre-press corrections. 3. The dot gain value Z sub d in actual printing is related to the following factors. Number 1. The thickness of the ink film of the impression. Number 2. The depth of the printing plate. Number 3. The flow performance and emulsification degree of the ink. Number 4. The printing pressure and the nature of the packing. Number 5. The pressure of the inking roller. Number 6. The transfer method, direct printing or indirect printing. Number 7. The compressibility of the blanket, etc. 4. Dot gain is the result of the combined action of two factors. Number 1. Mechanical dot gain. The actual area of the image and text ink film per unit area on the substrate is larger than the area of the image and text in the corresponding area on the original plate or printing plate, which is caused by the spreading of the image and text ink film to the surroundings under the action of pressure. Number 2. Optical dot gain, light bleeding. Due to the objective existence of the ink film thickness around the edges of the image and text. Although the ink film thickness is usually very thin, generally at the micron level, it makes the visual area of the image and text larger than the actual area of the image and text on the substrate. This is because of the shadows formed by the existence of light bleeding around the edges of the image and text. 5. The difference between the dot gain value Z sub d and the dot gain rate. During the printing process, the dot gain value Z sub d is more significant in terms of technology than the dot gain rate, because the dot gain value Z sub d is the basis for pre-press correction of the dots of each tone level. Fourth, the significance of measuring and controlling the dot gain value Z sub D as the basic unit of the image and text pixels. The dots will inevitably increase when transferred from the printing plate to the surface of the substrate, whether it is light bleeding or mechanical dot gain. If Z sub D is not measured and controlled, the tone of the printed product will deviate significantly from the original. As shown in the figure, the 50% dots on the printing plate become 65% dots when transferred to the substrate. The 95% dots on the printing plate become 100% solid areas when transferred to the substrate, etc. The actual curve during dot transfer is an arc above the ideal transfer curve. Therefore, under the condition that all printing conditions are clear, the measured actual dot transfer curve is of great significance for the calibration of dot replication in the high, middle, and low regions before plate-making printing. It also plays a very important role in the three-point measurement and control of dot transfer during proofing and printing. The application of the dot gain phenomenon in the signal block section, according to the delta value measurement and control method of dot gain, under the condition that the dot shape and dot area coverage are the same. The higher the screen line count, the larger the dot gain value. Therefore, the JTF digital signal strip makes use of this phenomenon. The 10 digits from 0 to 9 are composed of dots with a screen line count of 80 lines per centimeter. The densities of the 10 digits are different, decreasing step by step from 0 to 9. This digit is placed in a substrate composed of uniformly sized dots, with a screen line count of 26 lines per centimeter. Among them, the density of the digit 2 is always the same as the background color density, whether it is a positive image or a negative image. Therefore, under normal circumstances, the digit 2 is difficult to be recognized by the eyes. The dot coverage rate of the digit 2 is 50% under normal conditions during the printing process. If dot gain, delta, is positive, or dot shrinkage, delta, is negative, occurs, the value consistent with the background color density will move towards a digit greater than 2, dot gain, or a digit less than 2, dot shrinkage. Between the digits 7 and 9, each time it moves one level, the dot coverage rate changes by more than 5%. Between 0 and 7, each time it moves one level, the dot coverage rate changes between 3% and 5%. Similarly, for the JTF star target signal strip, the expansion width S of its wedge-shaped line essentially corresponds 1-to-1 with the delta value. This concludes today's lesson.